Hello everyone. This is Simardeep Singh, and this is my submission for the video PPT assignment. And my topic is the duality property of Fourier transform. So let's have a look at this. So first, what we need to look at is what is actually Fourier transform. So Fourier transform is a mathematical tool like which we use to analyze signals in the frequency domain, that is observing the signal variations with change in frequency. At the in the right side of the screen you can see various signals and their Fourier transforms. So Fourier transform exists only for the following signals. These are energy signals, power signals, and for these we need to use the properties of Fourier transform, as these are not absolutely integrable, and these properties will look further in the next slides. And third is impulse related signals. However, for signals that are neither energy and nor power, the Fourier transform does not exist. Mathematically, Fourier transform representation is given below, where x of j omega is equal to integral of minus infinity to infinity x of t e to the power minus j omega t dt is the mathematical representation. So now let's have a look at the properties of Fourier transform. So it has the following properties. Number one is linearity, that is the Fourier transform of sum of two or more functions is the sum of Fourier transforms of the functions. Scaling, if we stretch a function by a factor in time domain, then we squeeze the Fourier transform by the same factor in the frequency domain. Number 3 is differentiation. Differentiating function with respect to time yields to the constant multiple of its initial function in the frequency domain. Number 4 is convolution. The Fourier transform of a convolution of two functions is the pointwise product of their respective Fourier transforms. And number 5 is frequency shift. Number 6 is time shift, which is the time shifting property concludes that a linear displacement in time corresponds to a linear phase factor in the frequency domain. The last property that we have is the duality property of Fourier transform, and that property we'll be discussing about that in the upcoming slides. So what is duality property? So for explaining duality property, suppose we have a function small xt with its Fourier transform being capital X of omega. Then the duality property states that if we have a new that if we form a new function of time that has the functional form of the transform capital F x of t, it will have the Fourier transform small x of omega that has the functional form of the original time function, but now it is in the function of a frequency. So mathematically it can be described that if small xt has a Fourier transform capital X of omega, then the capital XT will have a Fourier transform of 2 pi small x minus omega, where these double arrows suggest Fourier transforms. So now let's have a look at the proof of this property. So for proof, we know that using inverse Fourier transform we can get the function small x of t from its Fourier transform, that is capital X of omega. Thus taking using x of t is equal to 1 by 2 pi integral capital X of omega e to the power j omega t d omega, and changing t with minus t we get the following equation, and taking 2 pi to the other side we get 2 pi x of minus t integral from minus infinity to infinity capital X of omega e of minus j omega t d omega. Now if we replace t with omega and omega with t, we get the equation 2 pi x of minus omega is equal to minus infinity to infinity integral capital X of t e to the power minus j omega t dt. And on the right side you can see that this is the formula for Fourier transform of capital X of t. Thus we have proved the duality property is capital X of t has the Fourier transform 2 pi and small x of minus omega. Here we can see a visual example of duality property, where the Fourier transform of a rectangular sin C pulse and vice versa, the inverse Fourier transform converts the curve back to the square on the left. So this image has been sourced from the paper given in the slides. So in the above example, we can see the duality property in use. So let's talk about the benefit and or the use of duality property. So the main benefit of the duality property is that it allows the Fourier transform of signals for which we already have a Fourier pair, and that would be difficult to obtain directly. It is thus one more method to obtain the Fourier transform besides the Laplace transform and the integral definition of Fourier transform. For example, take a function x of t is equal to a sine c 0.5t. The Fourier transform of this signal cannot be found using the Laplace transform or the integral definition of the Fourier transform. Thus, the duality property provides a way to obtain it, as we talked earlier. So thank you. This was all from my side. Hope you found this presentation informative. Thank you.